Every year, over 1 billion feet of steel chains are produced worldwide, from those that lift sea cranes to those that support bridges. But only a few of them go through a journey where precision is measured in microns, and every spark during welding is the beat of a metal heart. Imagine, a piece of ordinary steel transforms into a link capable of withstanding tens of tons. How exactly? In a few minutes, you will see how a force that cannot be broken is born. And if you watch until the end, you'll learn the secret that determines whether a chain will survive under maximum load. Our journey begins not in the noisy workshops, but much earlier, in the design office. It is here, at the design stage, that engineers determine what our chain will be like. What is it intended for? What loads must it withstand? Will it operate in an aggressive environment? The answers to these questions dictate the choice of material. In the vast majority of cases, for the manufacture of welded chains used in lifting mechanisms, industry, construction, or as fastening elements, we use high-quality steel rod. Take a look at these warehouses. Here they are, our round bars, thick, heavy, shining with strength. They can have different diameters, from a few millimeters for light chains to tens of centimeters for true giants that lift tons of cargo. Each batch of rods undergoes a thorough incoming inspection. The metallurgical laboratory checks the chemical composition of the steel, its mechanical properties, tensile strength, impact toughness. This is critically important, as the safety and reliability of the final product depend on the quality of the raw material. Only rods that meet the highest standards are allowed for further processing. This is the first, but extremely important, step in ensuring the unsurpassed quality of our chains. So, our selected steel rod is ready for transformation. The next stage is cutting. Here, high-precision cutting machines come into play, which, like surgeons, cut long rods into sections of a perfectly specified length. These sections will become our future links. Every millimeter matters, as the uniformity and correct geometry of the entire chain depend on the cutting accuracy. Operators carefully monitor the process, controlling the dimensions of each blank. And now we move on to one of the most spectacular stages: forming the link. Look at this powerful machine. It's an automatic press or a special bending unit. The metal section, heated to a plastic state, and sometimes without preheating if the diameter and steel grade allow, is fed inside, and under colossal pressure or a complex bending motion, it is transformed. Before our eyes, a straight rod is bent into a perfect oval or round shape, the future link. It is important that the ends of the rod are not completely joined, leaving a small gap, a seam. This seam will be a key element for the next stage. The newly formed link is fed to a mechanism that threads it through an existing link of the chain. It's like an amazing dance where one part is woven into another, creating a single whole. And now, the most important moment: welding. Most often, electric resistance welding, or flash butt welding, is used for chains. This is a high-tech process where the ends of the link that form the seam are clamped between electrodes. A powerful electric current is passed through them, which instantly heats the metal to its melting point. See those bright flashes? The fountains of sparks? That's the metal melting. And then under the pressure of the electrodes, an upset occurs. The ends are joined, forming a strong, homogeneous weld. In some cases, especially for very large chains, arc welding may be used, but the principle remains the same, creating an unbreakable metal joint. This weld is not just a connection. It's the weakest point of the link, and it is here that its future strength is established. Welding masters are true virtuosos, as the integrity of the entire chain depends on their work. After welding, the excess metal can be trimmed or processed for smoothness. The newly formed and welded chain, although strong, has not yet revealed its full potential. To meet the highest requirements for strength, durability, and safety, it goes through a series of finishing processes. The first of these is calibration. The long chain passes through special dies under pressure. This ensures the precise dimensions of each link, eliminates minor deformations after welding, and gives the chain uniformity. A calibrated chain will be ideal for working with sprockets and other mechanisms where precision is critical. After calibration, the chain heads to the heart of the factory: heat treatment. This stage is one of the most important and determines the final mechanical properties of the chain. Depending on the steel grade and desired characteristics, the chain may undergo several operations. Let's talk about each of them separately. Quenching. The chain is heated to a high temperature in special furnaces and then rapidly cooled in water, oil, or a polymer solution. This makes the steel very hard but brittle. Tempering. To eliminate the brittleness after quenching and increase the ability to absorb impact energy without breaking, the chain is heated again, but to a lower temperature and cooled slowly. This process gives the chain the necessary balance between hardness and ductility. Normalizing. Sometimes, instead of, or in addition to, quenching and tempering, normalizing is used, heating to a certain temperature, followed by cooling in air. This improves the metal's structure and relieves internal stresses. All these processes are carefully controlled by computer systems, as even a small change in temperature or holding time can significantly affect the final result. Heat treatment is a true art of controlling the properties of metal. After heat treatment, the chain comes out of the furnace, but its journey is not yet over. At this stage, it may have scale on it, a layer of oxides formed at high temperatures. Therefore, the next step is cleaning. This usually happens in special shot blasting chambers. Thousands of small metal shot particles under high pressure bombard the surface of the chain, knocking off scale and other contaminants. The result? The chain becomes clean, smooth, with a pleasant metallic sheen, ready for the next stages. In order for our chain to serve long and reliably even in difficult conditions, it needs protection from corrosion. This is where coating comes into play. The most common method is galvanizing, which can be hot dip or electroplating. In hot dip galvanizing, the chain is immersed in a bath of molten zinc at a temperature of 860 degrees Fahrenheit. Zinc, interacting with steel, forms a strong protective coating that not only prevents rust, but also has the property of self-healing for minor damages. In electroplating, the chain is placed in an electrolytic solution, and under the action of an electric current, zinc deposits on the surface of the steel. This coating is thinner, but gives the chain a more aesthetic appearance. In addition to galvanizing, other types of coatings may be used. For example, polymer paints, or special anti-corrosion compounds, depending on the purpose of the chain. We are approaching the final stage, and this is perhaps the most responsible moment: testing. It is here that our chain confirms its readiness to perform the most complex tasks. Every single chain undergoes a whole complex of checks for compliance with international safety and quality standards. Look at this huge test stand. Here the chain is subjected to colossal loads. It is stretched with a great force, which significantly exceeds its nominal working load, but at the same time does not reach the breaking point. This is the so-called proof load test. During this process, possible hidden defects and weak points that could manifest during operation are revealed. If the chain successfully passes this test, it means that it will withstand the declared loads and ensure safe operation. In addition to this, other types of control are carried out. Specialists carefully inspect each link for cracks, deformations, quality of welds, and coating. With the help of special calipers and measuring instruments, the compliance of the link sizes, their shape, and the chain pitch with the specified parameters is checked. From each batch of chains, samples are taken, which are then subjected to breaking tests. This allows to determine the maximum breaking force that the chain can withstand and to make sure that it meets or exceeds the established norms. These are brutal but necessary tests that guarantee that the entire batch of products is reliable. Only chains that have successfully passed all stages of quality control without exception are given the right to leave the factory premises. Each batch is accompanied by a certificate of conformity, which confirms its characteristics and the passing of all tests. This is our guarantee, a guarantee that you are getting a product of the highest quality and reliability. And now, dear viewers, we see the final result. Chains of different sizes, diameters, with different coatings, neatly laid in coils, ready to be sent to all corners of the world. They will go to the construction of skyscrapers, to port cranes, to ships, to agriculture, to production lines, everywhere where unbreakable strength, reliability, and safety are needed. From small, elegant chains for decorative purposes to huge ones that lift bridges, each of them has gone through a long and complex path of transformation, from raw metal to a high-tech product. Every year, over 50 million tons of batteries are discarded worldwide, from small AA batteries to giant electric vehicle batteries. Imagine a mountain of metal reaching the size of Mount Everest, filled with toxic substances. But now, part of this mountain gets a second life. Behind the thick walls of factories, old batteries are put into shredders where steel blades tear them apart. They are frozen with liquid nitrogen and turned into a black powder that will once again become lithium or cobalt. Watch until the end. You will see how a new future for energy is born from waste. Battery collection starts with people. Private individuals turn in batteries from phones and laptops. Car service centers, batteries from electric vehicles, and also businesses that use a lot of equipment. Collection points are in electronics stores, supermarkets, or specialized collection centers. Here, everything is as manual as possible. People bring batteries, and staff or volunteers accept and record them. Old batteries from factories or car service centers are delivered by trucks to large collection centers. Special battery containers have sensors that determine the fill level. When a container is almost full, a signal is sent to the collection company. Some companies use drones to check the fill level of large containers in remote locations. Batteries are sorted by type by people and machines, because batteries come in different types: lithium-ion, nickel metal hydride, lead acid, and so on. They cannot be mixed during recycling. At small collection points, for example, in cities, batteries are sorted manually by workers. They rely on markings, labels, and appearance such as shape and case color. Small batteries from smartphones or laptops go in one direction, and large batteries from electric vehicles in another. At large enterprises, automatic sorting lines are in operation. Machines scan batteries by size, weight, and the type of metals they contain. X-ray analysis or spectroscopy is used to determine exactly which battery is in front of the machine. After scanning, the batteries move along a conveyor to different bins, where they await the next stage. Even at automated factories, people are present. Operators check whether the machines are sorting the batteries correctly. If a problem arises, for example, a torn battery case or a missing label, people intervene and sort manually. Batteries from electric vehicles or solar stations are too large for automatic lines. This is where robots come into play, helping to disassemble these giant blocks into smaller sections. Then they are sorted by material. No matter how much machines do, people are still the most important in the sorting process. These are mainly the workers at collection points and the operators of sorting lines. Specialists assess damaged batteries manually because machines cannot yet recognize all defects. Machines work faster, but for now, they can't do without people. Ultimately, every correctly sorted battery is a chance to recover rare earth metals and reduce environmental harm. Next, the batteries need to be shredded. They enter real metal jaws. The batteries are loaded into a machine that looks like a huge shredder, equipped with steel blades. The blades are so powerful that they can even shred the body of an electric car. Metal chaos ensues. The sound of tearing, grinding, and cracking. The batteries are literally ripped to shreds. Since the batteries can be charged, they first undergo freezing in liquid nitrogen. This cools the metals and reduces the risk of ignition. Some shredders operate in sealed chambers with inert gases to exclude contact with oxygen. There is also a more spectacular option. In some places, a controlled current is first used for ignition. The battery literally burns out, leaving only the metals. The batteries are shredded into pieces from a few centimeters to a crumb, depending on the type of shredder. The blades rotate at a speed of over 2,000 revolutions per minute, and metal fragments fly in all directions with a clang inside a protected chamber. The shredded pieces pass through magnetic separators, which, with filigree precision, extract ferromagnetic metals, for example, nickel or cobalt. Fragments of other materials continue their journey along the conveyor. A fine black powder, known as black mass, settles in special containers. This is where the treasures are hidden: lithium, cobalt, manganese. Machines literally suck up the powder with dust collectors to gather even the microparticles. Residues that are not suitable for recycling, meaning plastic and traces of electrolytes, are washed away with special streams of liquid. At this stage, hydraulic crushers are used, which turn the remnants into a slurry that is easy to filter. Engineers monitor the condition of the shredders and the temperature level inside the chambers. Specialists work with the results of the shredding. They check whether all the metals have been separated and whether any extra impurities remain. If a battery is charged and has defects, it can literally explode during shredding. But the system controls this. The explosion is extinguished by gases, and the process does not stop. After the batteries are shredded and that precious black powder is obtained, science in action, as they say, begins. The metals that seem to be hidden forever are extracted using two main methods: hydrometallurgy and pyrometallurgy. And although this may sound a bit technical, the processes themselves are extremely interesting. So what does it look like? Battery fragments are immersed in special acid solutions. There are huge tanks where a yellowish-green liquid is bubbling. This could be sulfuric or hydrochloric acid. During immersion, a reaction occurs. Lithium, cobalt, nickel, and other metals literally dissolve in this soup. To extract the desired metal, a clever trick is used: ion extraction. Special reagents, for example, organic compounds, are added to the liquid, which capture a specific metal, like a magnet. As a result, each metal settles into a separate layer. When the metals are separated, they are precipitated in the form of salts or hydroxides. They look like small white or colored crystals. For example, lithium precipitates as lithium carbonate, a powder that looks like fine sugar. Cobalt becomes a bright blue precipitate, and nickel, a pale green one. If hydrometallurgy is a gentle approach, then pyrometallurgy is more like shock therapy for metals. Here, everything literally burns and melts. The black mass is loaded into a huge arc furnace, where the temperature reaches almost 3,000 degrees Fahrenheit. The metals melt into a liquid mass, and the plastic and other residues simply burn up. The metals stratify like oil and water, but at the temperature of molten lava. Several layers form in the furnace. Heavy metals, meaning cobalt and nickel, settle to the bottom, while lithium remains in the slag. This is the upper, lighter layer. Then this slag is broken up and processed separately to extract the lithium. After cooling, the metals take the form of small ingots, shiny, smooth, and ready for reuse. The cooling after the pyrometallurgical process usually happens in a controlled manner. After all, if you just let the molten metals cool on their own, it could take hours and sometimes even days. In addition, such cooling can create an uneven metal structure. This will affect the quality of the final product. Therefore, they are usually cooled in special chambers, where the cooling rate can be regulated. If the controlled cooling is air-based, the ingots are left on a conveyor under powerful fans. It's like a giant hairdryer that quickly cools the metal surface. If it's water cooling, for a faster process, the metal ingots can be immersed in a bath of water or special liquids. This is a huge tank where the red-hot ingot, upon entering the water, releases clouds of steam. It looks quite spectacular. Sometimes there is combined cooling. This is when some stages begin with air cooling and then are completed with water cooling to reduce stress in the metal. Controlled cooling ensures a uniform structure of the metals, which is critically important for their reuse in batteries. This reduces cracks or defects that can arise from sharp temperature changes. The obtained lithium is used to create new batteries, those that will charge electric cars or even your phones. Nickel can become part of turbines that generate energy from wind, and cobalt, an important component of medical equipment. So we are literally closing the loop. Old batteries give life to new technologies. Discarded batteries can turn into a real environmental disaster. First, they contain toxic substances that pollute the soil and water. Second, the mining of new rare earth metals not only depletes natural resources, but also harms the environment. Recycling solves both of these problems. You know what else is cool? The more batteries we recycle, the less we depend on mining new materials. This is a direct path to sustainable development. Despite the popularity of lithium, only 1% of this metal is currently recycled. The main reason is the high cost and complexity of the process. But researchers are developing new technologies that could change the situation in the coming years. Interestingly, even now, electric car manufacturers like Tesla, Volkswagen, and BMW are investing in their own recycling plants to maintain control over valuable materials. Imagine a toxic gas that was once used as a weapon in war. Today, however, your plastic windows, the medicines in the pharmacy, or even your drinking water wouldn't exist without it. The United States produces over 12 million tons of chlorine each year, a capacity that could turn the ocean into a giant swimming pool in a matter of days. But the real mystery is something else. Only a tiny fraction of this volume is used for disinfection. So where does the rest go? Watch until the end, and you will learn a secret that will turn your idea of this gas upside down. The United States is one of the world's largest producers of chlorine. Annually, the country's factories produce over 12 million tons of this gas. This number is simply mind-boggling. Imagine the weight of the aircraft carrier Gerald R. Ford, the heaviest warship in the world. It's about 100,000 tons. This means that in a year, American industry produces as much chlorine as 120 such aircraft carriers weigh. This huge amount makes chlorine one of the 10 most produced chemicals in the country. It all begins not in a laboratory, but deep underground. The main ingredient for our recipe is ordinary rock salt, or sodium chloride. But it's not brought to the factory in salt shakers. It is either mined in the form of huge blocks, or, much more efficiently, pumped out from under the ground. Water is pumped into deep underground salt deposits. The water dissolves the salt, forming a saturated salt solution called brine. And it is this concentrated, salty as tears solution that is our raw material. But it's still dirty. It's full of impurities, calcium, magnesium, and other minerals that can clog our expensive equipment. So before the main show begins, the brine undergoes a thorough cleaning. It is passed through a whole series of tanks where, with the help of chemicals, all impurities are precipitated and filtered out of it. At the exit, we get a perfectly clean, transparent, and very salty solution, ready for the main event, electrolysis. Now let's move to the heart of the factory, to the so-called cell room. This is a huge, noisy hall, filled with rows of strange closed tanks, connected by a network of pipes and thick electrical cables. These are electrolyzers, or cells. It is here that all the magic, or rather, all the chemistry, will take place. Let's imagine one such electrolyzer. Essentially, it's a box into which our clean salt solution is poured, and two electrodes are immersed in this solution, a positively charged anode and a negatively charged cathode. And now, a direct electric current of colossal strength is applied to these electrodes. And here the breakdown begins. The salt molecule in the water breaks down into positively charged sodium ions and negatively charged chloride ions. and the electric field forces them to move. The positive sodium ions are attracted to the negative cathode like a magnet, and the negative chloride ions to the positive anode. And here, at the anode, what it was all for begins. Each chloride ion that has stuck to the anode gives up its extra electron. Two such chlorine atoms, having lost their charge, immediately unite, forming a molecule of gaseous chlorine. Billions of these molecules gather together, and tiny bubbles of a greenish-yellow gas begin to appear on the surface of the anode. This is our chlorine. The main resource for chlorine production is electricity. The chlor-alkali industry is one of the largest consumers of electricity in the entire US manufacturing sector. To produce 1 ton of chlorine, approximately 2,500 kilowatt hours of electricity are needed. And now let's multiply this by 12 million tons per year. It turns out that this industry consumes about 30 billion kilowatt hours annually. This is more than the annual electricity consumption of entire states, like Vermont or Wyoming. This is a city of 1 million people, working all year just to break salt molecules. But what happens at the cathode? The sodium ions have arrived there. But they do not turn into metallic sodium. Instead, the electric current splits the water molecules in the solution into hydrogen and hydroxide ions. Bubbles of pure hydrogen are released at the cathode. This is our first byproduct. And the hydroxide ions remaining in the solution combine with our sodium ions, forming caustic soda. This is our second, incredibly valuable byproduct. But here, a huge problem arises. We have just obtained 3 substances: chlorine, hydrogen, and caustic soda. And they must never be mixed. Chlorine and hydrogen together form an explosive mixture, and chlorine and caustic soda react to form bleach, which we don't need at all. Therefore, the whole genius of the technology lies in separating these 3 products at the moment of their birth. For this, special membranes or diaphragms are used. Imagine that between the anode and the cathode, there is a thin, paper-like, but very clever partition. This membrane, made of a special polymer, is like a face control at a nightclub. It lets the positive sodium ions pass through to the cathode, but blocks the negative chloride ions, not letting them into the cathode space. Thus, chlorine is born and collected in one part of the cell, and hydrogen and caustic soda in the other. Now we need to collect our harvest. From the anode chamber, a wet, hot, greenish-yellow gas is continuously pumped out. First, it needs to be cooled. It is passed through heat exchangers, where it gives up its heat. Then, it needs to be dried. Chlorine is incredibly aggressive, especially when wet. It corrodes almost everything. But there is one substance it doesn't touch: concentrated sulfuric acid. So the wet chlorine is passed through towers, where it bubbles through sulfuric acid, which, like a sponge, absorbs all the water from it. The resulting dry, cold, but still gaseous chlorine is ready for the next stage: liquefaction. It is compressed under huge pressure and simultaneously cooled. Under this double blow, the gas turns into a transparent, amber-yellow liquid, similar to oil. This liquid chlorine is much more convenient to transport and store. It is poured into special thick-walled steel tanks or railway cars. Every step of this process takes place in conditions of absolute hermeticity, because a leak of this gas is deadly. And what about our byproducts? They are no less important. The hydrogen we obtained is collected, purified, and used either as fuel for the plant itself or sold for the production of ammonia or in the food industry. And the resulting caustic soda solution is pumped out, concentrated by evaporating the excess water, and sold. This is one of the most important products in the chemical industry, used for the production of soap, paper, aluminum, and much more. And so, from simple salt water, by passing a huge amount of electricity through it, people have learned to obtain 3 extremely important substances at once, which are the foundation for thousands of other products that surround us in everyday life. And now, let's see where all this huge amount of chlorine goes. You might think it all goes to disinfecting swimming pools, but that's just a drop in the ocean. In fact, less than 5% of all chlorine is used for water disinfection. So, where does the other 95% go? It is a key building block for other products. About 40% of all chlorine goes to the production of this universal plastic. The vinyl windows in your house, water pipes, medical IVs, vinyl records, the credit card in your wallet, all of this was born thanks to chlorine. Another 40% is used to create thousands of other organic and inorganic compounds. Pharmaceuticals, solvents, refrigerants, herbicides, insecticides. The list is endless. And chlorine is also a key component for bleaching paper, giving it that same pure white color. And finally, about the byproducts, which are actually no less important. We remember that for every ton of chlorine, we get about 1,100 tons of caustic soda. This means that annually, American industry produces over 13 million tons of this important alkali. This makes chlor-alkali production a perfectly balanced business. When the demand for one product falls, the demand for the other may rise, allowing the plants to operate stably. So these millions of tons are not just statistics. They are proof that this sharp, suffocating gas is the invisible foundation for a huge part of the American economy, from the plastic pipes under our streets to the medicines in our pharmacies. Every year, humanity creates energy that on one hand saves cities, and on the other, hides an incredible story of transformations. One average reactor produces 1,000 megawatts and requires only 27 tons of enriched uranium per year, the weight of 3 school buses. But to get these 27 tons, you have to mine and process over 100,000 tons of ore. In this video, we will follow the path from a noisy mine and acid vats to supersonic centrifuges, furnaces, and tiny fuel pellets. Every step is chemistry, giant machines, and unexpected risks that you are almost never told about. Stay until the end, and I will reveal one secret to you that will change your perception of atomic energy. An average American nuclear reactor has a capacity of about 1,000 megawatts. For it to operate for 1 year, it needs approximately 27 tons of enriched uranium fuel. 27 tons is the weight of about 3 school buses. And now let's compare. To produce the same amount of electricity, a coal-fired power plant needs to burn over 3 million tons of coal. That's over 10 million barrels of oil. Nuclear fuel is the highest form of energy concentration that humanity has ever created. But to get these 27 tons of fuel, you need to start with a much larger amount of raw material. The chain of transformations is simply staggering. To produce those same 27 tons of enriched uranium fuel, you need to start with 215 tons of uranium concentrate. And to get those 215 tons of concentrate, you need to mine and process over 100,000 tons of uranium ore. Imagine a giant mountain of stone, the size of a multi-story building, which ultimately turns into a volume of fuel that fits in one truck. This shows how dispersed uranium is in nature and how complex the process of its concentration is. It all begins in the roaring chaos of a uranium mine. Imagine a deep shaft or a giant open-pit quarry where huge machines with a deafening roar bite into the rock. The air here is thick with dust, and every stone that is brought to the surface looks absolutely ordinary, just a gray, dull granite or sandstone. The uranium here is invisible. It is dispersed in the rock in the form of tiny microscopic inclusions, and its concentration is incredibly low, often less than 1%. This means that to get 1 pound of uranium, you need to mine and process hundreds or even thousands of pounds of barren rock. Dump trucks, loaded to the brim, take this ore to a nearby processing plant that hums. The first stop is the primary crusher. This is a giant steel maul that, with a deafening crunch, crushes large stone blocks into pieces the size of a fist. Then, this crushed stone goes by conveyor to a huge mill. A giant rotating drum, filled with steel balls, resembles an industrial washing machine for stones. Here, in a continuous roar, the ore is ground into the finest, grey sand, almost dust. And now the real chemistry begins. a process called leaching. This grey sand is mixed with water, forming a thick pulp, and pumped into huge vats the size of a small house. A powerful chemical solvent is added to these vats, most often sulfuric acid. This acid, like a hungry predator, begins to eat the uranium, pulling it out of the solid rock and turning it into a liquid, dissolved state. This process lasts for many hours, while the entire mixture is continuously stirred. As a result, we get two things. On one hand, tons of wet, now unnecessary sand, so-called tailings, which are toxic waste, and on the other, a murky, greenish-yellow liquid containing our precious uranium. This liquid needs to be cleaned and concentrated. It is passed through a series of columns filled with special ion exchange resins. Imagine this as a high-tech water filter. The resins, like a magnet, pull out only the uranium ions from the solution, letting everything else pass by. Then these resins are washed with another solution, which washes the concentrated uranium off them. And so, finally, our final product is precipitated from this clean, saturated liquid. By adding ammonia or hydrogen peroxide, the uranium is forced to fall out of the solution in the form of a bright yellow, thick precipitate. This precipitate is filtered, dried in furnaces, and at the output, we get the same famous yellow cake, a heavy, radioactive, mustard-like powder. This is the uranium oxide concentrate, the first step on the long path to clean energy. The next step is purification to an absolute, almost unearthly purity. The yellow cake is sent to a special plant, where it is dissolved and, with the help of complex chemical processes, such as solvent extraction, all impurities are removed from it. The goal is to obtain perfectly pure uranium dioxide. But here the main problem arises, which is at the heart of all nuclear energy. In this perfectly pure uranium, 99.3% is the stable, lazy isotope uranium-238, which cannot sustain a chain reaction. And only 0.7% is the energetic, unstable isotope uranium-235, which is our fuel. They are chemical twins, and it is impossible to separate them by chemistry. To make the reactor work, we need to increase the concentration of this energetic uranium-235 from 0.7% to 3 or 5%. To begin enrichment, the solid uranium must be converted into a gas. It is treated with hydrofluoric acid, turning it into uranium tetrafluoride, and then with fluorine to obtain uranium hexafluoride. This is a very corrosive and dangerous compound, which has a unique property. It becomes a gas at a temperature slightly above room temperature, and so this gas, packed in special containers, is sent to an enrichment plant. Imagine a giant, noisy workshop the size of several football fields, filled with thousands of identical, tall, metal column-like devices. These are gas centrifuges. Each of them is a high-tech top that rotates at supersonic speed, making tens of thousands of revolutions per minute. When our uranium gas is pumped inside, the magic of physics begins. The heavier gas molecules with uranium-238, under the action of centrifugal force, are pressed against the walls of the centrifuge, and the very slightly lighter molecules with uranium-235 remain closer to the center. This is a microscopic difference, but it is enough. Special tubes take the gas from the center, which now contains a little more uranium-235, and send it to the next centrifuge in the cascade. And the depleted gas from the walls is diverted to the side. To achieve the required concentration of 3 or 5%, the gas must pass through thousands of such centrifuges. This is an incredibly long and energy-intensive process. When we have finally obtained our uranium hexafluoride, enriched to the required level, it needs to be converted back into a solid material suitable for fuel. With the help of chemical reactions, it is turned into a black powder of uranium dioxide. But this is not just any powder. Each of its particles has a perfectly calibrated size and shape. Now the most interesting part begins, the creation of fuel pellets. This black, heavy powder is sent to a press. Imagine a high-precision pharmaceutical press, only instead of medicine, it stamps radioactive pellets. It compresses the powder with incredible force, turning it into small, dense, perfectly cylindrical granules, or pellets. They are still brittle, like chalk. To give them strength, they are sent to a furnace. But this is not an ordinary furnace. This is a high-temperature furnace, filled with hydrogen to prevent oxidation. There, at a temperature of over 3,000 degrees Fahrenheit, these pellets are baked for many hours. During this process, called sintering, the powder particles fuse together, and the pellet turns into an extremely hard, dense, ceramic-like substance. It becomes so strong that it can withstand the extreme temperatures and pressures inside a nuclear reactor. Each pellet after this undergoes laser control, which checks its dimensions with micron accuracy. The next step is assembly. These small black ceramic candies are carefully, one by one, loaded into long, thin tubes. These tubes, about 13 feet long, are not made of steel, but of a special zirconium alloy called zircaloy. This material is unique in that it is very strong, resistant to corrosion, and most importantly, almost transparent to neutrons, allowing the chain reaction to proceed without hindrance. When the tube is completely filled with pellets, it is filled with an inert gas, usually helium, to improve heat transfer, and hermetically sealed at both ends. Now, it is not just a tube with pellets, it is a fuel element. And the final stage is the creation of a fuel assembly. Several hundred such ready-made fuel elements, for example 17 by 17, which gives a total of 289 pieces, are assembled into one large square bundle. They are held together by special spacer grids. This ready-made assembly, which looks like a giant, high-tech quiver with arrows, is the final product. It weighs about half a ton and is ready for shipment to a nuclear power plant. And so, having passed an incredibly long and complex path from an ordinary stone through chemical transformations, supersonic rotation in centrifuges, infernal baking, and precise, almost clockwork assembly, this concentrated bundle of energy is born, ready to quietly and reliably produce millions of kilowatts of clean electricity for several years. Imagine thousands of glass threads, thin as a hair, combined into a single river, are transformed into a material that is already challenging steel. This isn't science fiction, but modern production of fiberglass rebar. Every year, the world spends billions fighting rust, repairing bridges and parking garages destroyed by corrosion. But there is a solution, a composite that is twice as strong as steel, 4 times lighter, and doesn't even know what rust is. The market for this material is growing by 12% annually, and today you will see how a building material of the future is born from hundreds of bobbins and a barrel of resin. It all begins at one end of a huge workshop, where a structure resembling a giant library for threads stands. This is called a creel. On a wall, several yards high, hundreds, and sometimes thousands, of huge bobbins are installed in neat rows. On each of them is wound the thinnest glass thread, or roving. This isn't the glass that windows are made of. This is a special fiberglass, which is produced by melting glass and drawing it through microscopic holes. The result is threads thinner than a human hair, but with incredible tensile strength. They will be our skeleton, our internal army, which will give the rod its insane strength. From each of these hundreds of bobbins stretches its own separate thread, and they all gather into one thick, fluffy bundle. It's like thousands of streams merging into one large river. This dry white bundle is the soul of the future rebar. Next, this river of fiberglass begins its journey. It passes through a system of guides and tensioning devices. This is a very important, though inconspicuous, stage. Each of the thousands of threads must be tensioned with the same force. If one thread sags and another is over-tensioned, the load in the final product will be distributed unevenly, and it will lose its strength. Therefore, the machine carefully aligns them, preparing them for the most important moment baptism in resin. The dry glass bundle is slowly immersed in a bath filled with a thick, sticky liquid, similar to honey or syrup. This is a polymer resin, our meat, that will grow on the glass skeleton. This is a complex chemical cocktail. The base is usually polyester, vinyl ester, or epoxy resin. A hardener is added to it, a catalyst that will start a chemical reaction and force the liquid to turn into a solid plastic. Also, various additives can be added here. Pigments to give color, ultraviolet inhibitors so that the rebar is not afraid of sunlight, and flame retardants for fire resistance. The task of this bath is to soak every, even the tiniest fiber. The bundle must be completely submerged in this resin so that not a single dry spot remains. The soaked, heavy from sticky resin bundle comes out of the bath and heads to the point of its birth, the forming die. This is the heart of the whole process. Imagine a thick steel plate with a perfectly round, polished hole, the diameter of which exactly corresponds to the diameter of the future rod. The die is heated to a certain temperature. When the wet bundle is drawn into this hole, several things happen at once. First, the die, like a press, squeezes out all the excess resin, leaving only the necessary amount. Second, it tightly compresses all the fiberglass together, forming a perfectly round rod. Third, the heat from the die starts the initial stage of the chemical reaction of hardening, or polymerization. The resin begins to turn from a liquid into a gel. At the exit of the die, we already see the familiar shape of the rod, but it is still soft and vulnerable. But how does it get its famous ribbed surface to hold well in concrete? Immediately after exiting the die, while the rod is still hot and soft, a special bundle of the same fiberglass is wound onto it. A thin, resin-soaked thread is wound in a spiral on the surface of the rod, creating a relief pattern. Sometimes, for even better adhesion, fine quartz sand is sprinkled on the sticky surface, which sticks firmly to the resin. Now our rebar has not only strength, but also teeth with which it will hold onto concrete. The formed and wrapped rod enters the longest part of the machine, the curing tunnel, or polymerization furnace. This is a long chamber that can stretch for tens of feet, inside which a high temperature is maintained, usually 400 Fahrenheit. Here, the final transformation takes place. This is not just drying. Under the influence of heat, the resin molecules begin to actively connect with each other, forming a strong, rigid, three-dimensional network. The liquid, sticky syrup turns into an extremely strong and hard composite material, which firmly binds millions of glass fibers into a single monolith. It's like baking a pie. While the rod slowly moves through this hot tunnel, it acquires its final, stone-like hardness. But what pulls it through this whole long path, from the bobbins to the furnace? At the end of the line stands a special pulling device, which gave the whole process its name. Usually, these are two caterpillar mechanisms, similar to tank tracks, located one above the other. They gently but very firmly clamp the already finished hard rod with their rubber pads, and at a constant, precisely calibrated speed, pull it towards themselves. It is they who create the force that pulls the fiberglass through the resin bath, through the forming die, and through the furnace. The speed of this movement is one of the most important parameters that controls the quality of the final product. And so, from the other end of this long conveyor appears an endless, perfectly even, hard and hot fiberglass rod. The final chord is cutting. Across the line is an automatic saw. It synchronizes with the speed of the rod's movement, at the right moment makes a quick forward movement, and with a sharp whiz, cuts off a piece of standard length from the endless ribbon. For example, 20 or 40 feet. Then it returns to its starting position, waiting for the next section to arrive. The finished, still warm rods roll onto a cooling table, and then they are collected into bundles, tied, and sent to the warehouse. And so, before our eyes, thousands of fragile glass threads and a barrel of sticky liquid, having passed through baths, presses, and furnaces, have turned into a light but incredibly strong building material of the future, ready to challenge rust and time in the concrete jungles. The fiberglass rebar market is not yet a giant like the steel market, but it is the coolest and most daring newcomer at the party, rapidly gaining popularity. The global market for this material is already valued at hundreds of millions of dollars, and the forecasts are simply insane. It is expected to grow by 10 or 12% annually. This means that more and more engineers and architects are looking at rusting steel and saying, "Dude, we can do better." And now about the main features that make steel rebar nervously smoke in the corner. The first and most obvious is weight. Fiberglass rebar is about 4 times lighter than steel of the same diameter. Sounds boring? Now imagine it in real life. Imagine a truck carrying rebar to a construction site. It can bring 4 times more length of fiberglass rebar in one trip than steel, because it is limited by weight. Or, for the same amount, it will take 4 times fewer trips, which saves fuel and time. On the site itself, 2 workers can calmly carry whole coils or bundles of fiberglass rods, whereas a crane is needed to move steel. This is a colossal saving on logistics and labor. Second is strength, and here fiberglass simply enters the ring and knocks out steel in the first round. Its tensile strength is about twice as high as that of standard steel rebar. So you understand, to break a fiberglass rod, you need to apply twice as much effort as for a steel one of the same diameter. This means that in some structures, rebar of a smaller diameter can be used, saving even more weight and volume. It's like comparing an ordinary rope with a climbing rope. At a smaller thickness, it withstands much greater loads. But the main trump card, the real superpower of fiberglass, is its war with rust. The main enemy of any reinforced concrete structure, from bridges to parking garages, is not the load, it's rust. Water and salts penetrate through micro cracks in the concrete, reach the steel rebar, and it begins to rust. Rust increases in volume and literally tears the concrete from the inside. Annually, the United States spends billions of dollars on repairing bridges, parking garages, embankments, and tunnels destroyed by rebar corrosion. And fiberglass? It just laughs in the face of rust. It is chemically inert. It is completely indifferent to water, salt, acids, and alkalis. This means that the service life of the structure increases dramatically. A concrete structure reinforced with steel is designed for more than 50 years, and a structure with fiberglass rebar is calmly designed for more than 100 years. Every year, over 400 million tons of paper are consumed worldwide. That's more than the weight of all the airplanes ever built by man. But have you ever wondered where this white sheet, on which we write, print, or package goods, comes from? It all begins with raw wood, which machines strip of its bark, shred into even chips, and send to giant boilers, where pressure and temperature transform the solid log into delicate cellulose fibers. This is not just production, it's the alchemy of modern times. And at the end of the video, I will reveal a secret that will change your perception of paper forever. The preparation of raw materials for paper production is a very important and interesting stage that lays the foundation for the quality of all the paper we later get. It begins with bringing the wood into a state convenient for further processing. First, Large timber is delivered to the paper mill, where it is debarked. The reason is simple. The bark is not needed. It contains many impurities that spoil the quality of paper and create problems during cooking. To remove the bark, special machines, debarkers, are used. These are large rotating drums or hydraulic systems that, like real tigers, strip the bark from the wooden logs without damaging the wood itself. It's like a thorough scrub for the wood. The amount of bark can reach 15% of the log's weight, so removing it is not just necessary, but it also significantly improves the subsequent process and the final quality. After cleaning the wood from the bark, it is shredded into small pieces, which in the paper industry are called chips. Special mechanical chippers are used. These are machines with a large number of sharp knives that quickly and evenly cut the logs into small chips, approximately 1 and 2 inches long. It's like chopping firewood in half, only on a much smaller scale. It is important that the size of the chips is as uniform as possible. If the pieces are too large or uneven, then during the next stage, cellulose cooking, individual parts will be processed unevenly, which will affect the quality and strength of the paper. Therefore, the chippers are adjusted to maintain maximum stability of the chip size. Immediately after shredding, the chips are fed into cooking boilers. But before that, they are often moistened or slightly steamed to facilitate the softening and dissolution of wood components, such as lignin. These steps also improve the energy-saving characteristics of the process. One of the tricks is that the bark contains various minerals and substances that can contaminate the cellulose, create problems in chemical reactions, and disable the equipment. So, thorough cleaning helps not only to get a cleaned raw material, but also makes the cooking process more stable and of higher quality. Thus, how clean and strong the cellulose mass will be depends on the removal of the bark and the shredding of the wood. To make one medium-sized roll of paper, you need to process several hundred pounds of wood, so every step in the preparation is very important. After the wood in the form of chips enters the huge boilers, it is placed in special reactors, where it is boiled in an aqueous solution of a sulfuric lignin-removing alkali. Most often it is caustic soda and sodium sulfide. Usually, the cooking temperature reaches about 300 degrees Fahrenheit, and the pressure can exceed 15 atmospheres for the process to be effective. The chemical reagents dissolve lignin, the substance that glues the wood fibers together. At the same time, the wood fibers remain practically undamaged, which is important for the quality of the future paper. At the same time, other undesirable components that can affect the color, strength, and texture of the paper are also removed. This process is called sulfate, or craft cooking, and it ensures the production of the strongest and cleanest cellulose among all methods. For different types of paper, the proportions of chemical substances, the time, and the cooking temperature may differ, depending on the type of raw material and the required quality of the final product. After the cooking is complete, the cellulose suspension is cooled, washed to remove the remaining reagents, and sent for further cleaning, removal of residual impurities, and refining. To eliminate the foam that forms during this process, special defoamers are used. After cooking the cellulose, when most of the lignin has already been removed, the paper mass usually has a yellowish or brownish tint due to residual impurities. This is where the bleaching process comes into play. Bleaching is designed to make the cellulose white or as light as possible, which is especially important for printing paper, colored cardboard, or high-quality office products. Most often, modern chlorine-free bleaching technologies are used, which are more environmentally friendly and do not form dangerous organochlorine compounds. Chemical reagents, such as hydrogen peroxide, ozone, sodium dithionite, or oxygen, gradually oxidize or reduce the colored components, thus lightening the mass without destroying the fibers themselves. In general, this is a fine balance, as too aggressive bleaching can worsen the strength of the paper. In addition to bleaching, at this time, deep cleaning of the cellulose suspension from small impurities, residues of paint, metal particles, resins, which can affect the color and quality of the product, takes place. For this, flotation units are used, where impurities, due to the difference in specific gravity and surface properties, are separated from the mass and removed. After this treatment, the cellulose mass becomes light, clean, and homogeneous, ready for the next stage of forming thin paper sheets. The formation of a paper web is the moment when the cellulose mass, consisting of fibers and water, becomes the paper itself. The process takes place on special equipment, a paper-making machine that has a processing screen. The cellulose suspension is evenly distributed over a large metal screen, which continuously moves forward. Through the openings of the screen, water begins to drain down, reducing the moisture in the paper mass. The fibers, in turn, are retained and begin to form a thin but strong layer. This thin layer, the future sheet of paper, continuously moves together with the screen to a complex of presses and drying rollers. Here, the remaining water is finally squeezed out. The paper is heated and acquires the required density and texture. After completing these stages, the thin and strong sheet of paper continues its journey to layer-by-layer processing and cutting. After forming a thin layer of cellulose mass, the process of pressing and drying begins. First, the paper sheet passes through the press section of the machine. Here, 2 or 3 heavy rollers press the thin layer, squeezing out the excess water. It's similar to wringing out a wet cloth. Pressing increases the density of the paper and prepares it for the next step. The moisture after the press is reduced to about 45%. Next, the sheet moves on to the drying rollers, large cylinders heated by steam, the temperature of which can reach 300 degrees Fahrenheit. The paper passes between these rollers, and the heat quickly evaporates the remaining moisture. The moisture exits through the open pores of the paper and drains into a condensate collection system. This stage is very dynamic. The paper sheet can move at a speed of several hundred meters per minute, quickly drying, but at the same time retaining its flexibility and strength. After drying, the paper becomes strong, smooth, and ready for further calibration and cutting. If necessary, the sheets pass through calendars, mounted pairs of rollers that give the paper a smooth shine and even thickness. After drying, the paper sheet passes through a pair of large, heavy, and very fast rotating steel rollers. This is called a calendar. These rollers press on the paper with great force, literally rolling it, to even out the thickness and give it a shiny surface. The temperature of the rollers can be very different depending on the type of paper, from about 80 degrees to over 500. The heat helps the fibers to melt a little, which improves the smoothness and strength of the web. With the help of calendaring, the paper becomes denser, more uniform in thickness, and also better suited for printing, as the ink lies on such a surface evenly and richly. The final stage of paper making is cutting and packaging. The finished paper roll, or a long ribbon, is fed to automatic cutting machines, where it is cut into sheets of standard or individual sizes, depending on the needs. For this, guillotines are used, large mechanical scissors that make an even and precise cut simultaneously across the entire width.